The state of the system. The system must be described in order to make any useful calculation by specifying quantitatively each of the properties such as its pressure, volume and temperature, as well as the composition of the system. So we need to describe the system by specifying it before and after the change. So you would recall from your physics course that the state of a system in mechanics is completely specified at a given instant of time by the position and velocity of each mass point of the system. In thermodynamics, a different and much simpler concept of the state of the system is introduced. It does not need detailed knowledge of motion of each particle because we deal with the average measurable properties of the system. So we specify the state of the system by state फंक्शंस और स्टेट वेरिएबल्स, राइट. सो हम क्या करते हैं कि थर्मोडायनेमिक्स में एक इनिशियल स्टेट और फाइनल स्टेट को कंसिडर करते हैं. द स्टेट ऑफ द सिस्टम is described by its measurable or macroscopic bulk properties. So we can describe the state of a gas by quoting its pressure, volume, amount, temperature, and so variables like pressure, volume, temperature are called state variables or state functions because of their values depend on the state of the system and not on how it reached. So in order to completely define the state of a system, it is not necessary to define all the properties of the system, as only a number of properties, certain number of properties can be varied independently. So this number depends on the nature of the system. Once these minimum number of macroscopic properties are fixed, the other automatically have definite values. The state of the surroundings can never be completely specified. Fortunately, it is not necessary to do so. तो इसलिए सिस्टम हम लेते ही उसी सिस्टम हम उसी पर्टिकुलर एक स्टेट को बोलते हैं जिसकी हम जो है जो स्टेट फंक्शंस हैं वो डिफाइन कर पाएँ, राइट, सो दैट वी कैन डिफाइन द सिस्टम. द इंटरनल एनर्जी एज ए स्टेट फंक्शन. So when we talk about a chemical system losing or gaining energy, we need to introduce a quantity which represents the total energy of the system. It may be chemical, electrical, mechanical, or any other type of energy you may think of. The sum of all these is the energy of the system. So in thermodynamics, we call it internal energy U of the system, which may change when heat passes into or out of the system, work is done on or by the system, and matters enters or leave the system. So these systems are classified accordingly. So first is the work. So what is work? So let us first examine a change in internal energy by doing work. So we take a system containing some quantity of water in a thermos flask or in an insulated beaker. This would not allow exchange of heat between the system and the surrounding through its boundary, and we call this system as adiabatic. Means जिसमें heat जो है exchange ना हो पाए, ना matter exchange हो पाए, that is the adiabatic. The manner in which the state of such a system may be changed will be called adiabatic process. Adiabatic process is a process in which there is no transfer of heat between the system and the surroundings. So here the wall separating the system and the surroundings is called adiabatic wall. So an adiabatic system which does not permit the transfer of heat through the boundary. So let us bring the change in the internal energy of this system by doing some work on it. So let us call the initial state of the system be A and its temperature as TA. Let the internal energy of the system in state A be UA. So we can change the state of the system in two different ways. So one way is we do some mechanical work, say 1 kilojoule, by rotating a set of small paddles and thereby churning water. So let the new state be called the state B and its temperature be TB. So it is found that TB is greater than TA and the change in temperature delta T is equal to TB minus TA. So let the internal energy of the system in state B is UB and the change in internal energy is equal to delta U is equal to UB minus UA. Second way, we now do an equal amount of, that is 1 kilojoule electrical work with the help of an immersion rod and note the temperature change. So we find that the change in temperature is same as the earlier way TV minus TA. So in fact the experiments in the above manner were done by J.P. Joule between 1840 and 50, and he was able to show that a given amount of work done on the system, no matter how it was done, irrespective of path, produced the same change of state as made by the change in the temperature of the system. So it seems appropriate to define a quantity, the internal energy U, whose value is characteristics of the state of the system, whereby the adiabatic W, adiabatic required to bring about a change of state, is equal to the difference between the value of U in one state and that in another state. Delta U is, that is, so delta U is equal to U2 minus U1 is equal to work adiabatic. Therefore the internal energy U of the system is a state function. Now by convention of IUPAC in a chemical thermodynamics, the positive sign expresses that W is positive, adiabatic is positive, and work is done on the system and the internal energy of the system increases. Similarly, if the work is done by the system, W adiabatic will be negative because internal energy of the system decreases. So can you name some other familiar state functions? Some of the other familiar state functions are volume, pressure, temperature. For example, if we bring a change in temperature of the system from 25 degrees centigrade to 35 degrees centigrade, the change in temperature is equal to plus degree centigrade, whether we go straight up to 35 degrees centigrade or we cool the system for a few degrees and then take the system to the final temperature. Thus temperature is a state function and the change in temperature is independent of the route taken. Volume of water in a pond, for example, is a state function because change in volume of its water is independent of the route by which water is filled in the pond, either by rain or by tubewell or by both. Now we can also change the internal energy of the system by transfer of heat from the surroundings to the system or vice versa without expenditure of work. So this exchange of energy, which is a result of the temperature difference, is called heat. So let us consider bringing about the same change in temperature, the same initial and final states as before, but transfer of heat through thermally conducting walls instead of adiabatic walls. So we take water at temperature TA in a container having thermally conducting walls, say made up of copper, and enclose it in a huge heat reservoir at temperature TB. The heat absorbed by system water Q can be made in terms of temperature difference TB minus T. In this case, change in internal energy delta U is equal to Q when no work is done at constant volume. So by a convention of IUPAC in a chemical thermodynamics, if Q is positive when heat is transferred from the surroundings to the system and the internal energy of the system increases, and Q is negative when heat is transferred from system to the surroundings and resulting in decrease of the internal energy of the system. So let us consider the general case in which the change of state is brought about both by doing work and transfer of heat. So we write the change in internal energy for this case as delta Q is equal to delta U is equal to Q plus W. So for a given change in state, Q and W can vary depending on how the change is carried out. So Q plus W is equal to delta U will depend only on the initial and final state. It will be independent on the way the change is carried out. So if there is no transfer of energy as heat or as work, isolated system W is equal to 0, Q is equal to 0, then delta U is equal to 0. So equation this 5.1 delta U is equal to Q plus W is mathematical statement of the first law of thermodynamics, which states that the energy of an isolated system is constant. So it is commonly stated as the law of conservation of energy, that is, energy can neither be created nor be destroyed.